So we mentioned earlier that we mentioned earlier that a linear line refers to a constant velocity where the velocity is not changing. And we focused on it and solved equations and problems using the first equation of motion, where the velocity is constant. Now, if for example the line were to curve or change, then it's then the velocity here is changing, and we refer to this change and it's known as acceleration. So acceleration is the change in velocity. And I want to highlight the point velocity because it's not the change in speed, it's the change in velocity. So change in velocity. So let's take a quick example here on acceleration. So we have a roundabout where we have a road, and then you go around the roundabout, and then continue your day on the road. So we have a car. It moves at a constant rate here. So a constant velocity at this point. And then it goes on the roundabout, right? It takes the turn and then goes back to its normal route. It doesn't go anywhere else. So my question to you is is the velocity changing at this point? And if it's changing, does that mean there's acceleration? So mentioned before that the acceleration is a change in velocity, meaning that velocity refers to magnitude plus direction. So the magnitude here, I'm gonna tell you that it continued to move at a constant rate of 60 meters per second throughout this entire trip, but I'm still gonna tell you that the acceleration changed. Why? Because the direction changed. You can see here that if this was north and this was south, here it moved from being only north to some kind of northeast, then back to north, then northwest, then north, and then continue to go north at a constant rate. So here the velocity is changing, meaning that meaning that the object is accelerating. Now we can also refer to acceleration to being the change in speed or magnitude. So an object slowing down, speeding up, so slowing down, speeding up, or even stopping. This is all acceleration, and we're going to solve a lot of questions on it. So bear with me, and we can understand acceleration. So in our first lesson, we used motion diagrams. So we used we used particle diagrams to denote motion. Now we had mentioned three different types. So constant motion, speeding up. So the diagrams would increase over time. So like here it'd be bigger, then it'd be bigger, and then here. And then it would also there's also one of them which was decreasing, or it was like slowing down, right? Slowing down. So it would get closer and closer to each other over time. Now, over here, it has constant velocity, right? It's constantly moving at a constant rate. So if it moved from 0 meters here to 6 meters, then to 12, then to 18, then to 24, then its velocity is constant, and this is constant acceleration. So constant velocity. So there's no acceleration. However, in this case over here, it moved 6 meters, so 0 to 6. Then it moved, I don't know, it increased, right? So it moved 14 meters here in this case, so +2. Then 6, 8, 10. So it moved 24. So the velocity is changing actually. It's not moving at a constant 6 meters per second. Here it's like 6 meters over here, and then it's 8 meters over here, then it's 10 meters over here, and then 36 meters over here. So here it's 12 meters. So it's increasing, and over time, there's more. There's the velocity is increasing, which is why this object over here is not at constant motion, but in acceleration. So the object is accelerating, and in this case over here, it moved from 0 to 6, and then it moved 6 meters in this case, and then it moved 10 meters, and then it moved for 12 meters, and then it moved 12 meters, and it continued to move 12 meters. So here you can see that the object moved 6 meters in the first one, so it's at 6 meters per second velocity, and then it's at 4 meters per second velocity, and then it's 2 meters per second, 2 meters per second. So the object is slowing down in this case over here, meaning that the acceleration is changing. So in this two and from this point to this point, the object is accelerating in the negative direction. So accelerating, but negatively, or you can say deceleration, but it's better to refer to it as acceleration. So it's negatively accelerating, right? Because it's slowing down. And then here, in this point, from this point to this point, it's at a constant velocity. So there's zero acceleration. So zero acceleration because there's no change in velocity. As we mentioned before, acceleration is the change in velocity. So when there's no velocity change, there's no acceleration. So when we talk about acceleration, during this entire chapter, or chapter or two, we're going to be referring to acceleration at a constant rate. So acceleration at a constant rate. So acceleration is constant at all times. We're not going to be covering the changing of acceleration or acceleration itself changing. Acceleration will be constant at all times. So let's look at this table over here. We'll draw a table, an XY table, with values of x and values of y. So y would be time. And we'll look over here. So y would be time, so time, and this would be uh, distance or x. So we'll look over here, and at 0 seconds, the object is at x equal to 0. Now, at 1 second, the object is at x equal to 2. So we move 2 meters in 1 second. However, at time is equal to 2, the acceleration or the object went 6 meters. And at time equal 3, uh, the object went 10 meters, 12 meters. And then at time equal 4, the object went 18 meters, or 20 meters in this case. So you can see that the object is not only changing positions and increasing the distance. The distance is sort of increasing more and more every single second. So if we look here, at 1 second, it changed by 2. And then in 2 seconds, it changed by 4. In 3 seconds, it changed by 6. And then in 12 seconds, and then in 4 seconds, it changed by 12 or 8. So every second, it's increasing, or the object is adding 2 plus more meters to its distance. And this is what we call acceleration. So the object is accelerating at a 2-second interval per second. And acceleration is denoted instead of saying meters per second. So instead of saying it's accelerating at 2 meters per second, we would say 2 meters per second squared. So the square differentiates between velocity and acceleration. So we talked about average velocity during the last lessons, but how would we calculate the average acceleration? So let's say an object accelerated from 0 meters to from 0 meters per second to 60 meters per second in 10 seconds. So it took the object 10 seconds to reach this velocity or this speed, or it should be velocity. So 6 meters per second, 60 meters. Now we can use the formula for average velocity, which is basically velocity average is equal to the velocity, so the change in velocity, which is this, over the time. And by doing this, we get 60 over 10, which is equal to 6 meters per second. And now, if if we're referring to acceleration, we need to add the square because acceleration's SI unit is meters per second squared, not meters per second. So how do we differentiate between velocity and acceleration? There's a square. We can actually plot this on a table. Like for example, we have an table over here, and we have time is equal to 0, right? So when time is equal to 0, then we have the initial velocity of, or the initial position of 0. And then time is equal to 1, we moved 6 meters as denoted by the acceleration. So 6 meters. Time is equal to 2, we moved 12. Time is equal to 3, we moved 18, and etc. Now, we can actually calculate the average velocity simply by taking the slope. So just take the slope of this, and we can do rise over run. So we do 12 minus 6. So obviously, this is x. Time is always the independent value, and this is a y. So 12 minus 6, 2 minus 1, and then we get 6, which is the acceleration. So we can calculate the slope of values, and we can calculate the change in change in velocity or the acceleration. So for this question, we have a bus, and it's moving west at 25 meters per second. So it's moving negatively 25 meters per second. When the driver steps on the brakes and brings the bus to a stop in 3 seconds. So he steps on the brakes and brings the bus to a stop in 3 seconds. So what is the average acceleration while braking? So firstly, uh we have to let's list out what we have. So we have velocity initially, which is equal to negative 25 meters per second squared, 25 meters per second, because it's moving west, right? Next up, we have uh, a negative acceleration because the value is braking, right? So we don't know the acceleration yet, but we'll calculate it. And then we have delta t, which is equal to 3 seconds. And since it brings the bus to a stop, v final will be equal to, so v final will be equal to 0 meters per second. Now, if we use the formula we stated at the beginning, which was acceleration is equal to delta v over time, then we'll be able to calculate it simply by breaking down delta v into v final, v initial, then over time. So let's just substitute it, and we'll get the answer. So negative 0 minus 25 meters per second over 3. Then we get 25 over 3, which is around 8.3 meters per second squared. Now, you may be wondering, why is it positive if it was braking, right? Well, if you remember earlier, it was mentioned that in the velocity time graph, we have two different things. We have when it's slowing down in the negative direction and slowing down in the positive direction. Now, if it's slowing down in the negative direction, that means that uh, that means that if the bus is like this arrow here, then if the bus is this arrow, so when the bus is slowing down, it's slowing down, slowing down, slowing down, right? So the arrow is getting shorter, and then it reaches a full stop. And since it was going to the negative direction, this is negative and this is positive, that means it was slowing down and also in the negative direction, meaning that it's negative times negative, meaning that the acceleration should have been predicted to be equal to positive. And if we were to draw the graph of this, of the velocity, it would be something that looks like this. Change the color. It would be something that looks along the lines of this, where the velocity is slowly but surely decreasing and becoming more positive, which is why the acceleration is positive. Now, for this next question, it's asking for uh, if it's asking this: if the bus took twice as long to stop, how would the acceleration compare to the value calculated in part A? So basically, twice as long, meaning that delta t would be equal to 2 times the value we got. So we got 3 seconds here, so delta t of the set of question B would be equal to 6 seconds. Now, with knowing this, how about we substitute it into the formula of acceleration? We have delta v, and then we have 2, so twice as long delta t. How would the value of a be? Well, because it's more practical to just substitute the values and give it instead of doing it theoretically, why don't we just do that? So we have 25, we already calculated here, over 6 seconds. And as you can see, because it's dividing it and halving the value of velocity, the answer should also be halved, meaning that instead of 8.3 meters per second, it would be around half of that, so 4.15 meters per second squared. So because it's inversely proportional to the acceleration, the time, that's why the value of acceleration is half. So this question is asking for the rate of a continent. It's saying that the rate of a continental drift were to abruptly slow uh, from 1 centimeter per year to 0.5 centimeters over the time interval of 1 year. So what would the average acceleration be? So let's simply state out what we have given. So we have abruptly slowed down, so it would be a negative acceleration. Or we can't really say that yet, but it's slowing down, so the acceleration is negative, but we don't know where the direction is, so we can't tell for sure yet. So we have uh, velocity, right? We have uh, we have v given. So v initial would be 1 meters or one centimeters, 1 centimeter per year, and 0.5 and v final would be zero point 0.5 centimeters per year. And we have the time interval, which is also 1 year. Now, as you can see, they're all the same units, so we're completely fine. We don't need to convert anything. Now, we can simply substitute into the formula delta v. So v is equal to delta t. So 0.5 minus, so remember it's v final minus v initial, so over time. So 0.5 minus 1 minus 1 over 1. Negative 0.5 over 1, which is also negative 0.5. So the acceleration is negative here. So A is negative 0.5 centimeters per year squared. To the topic of vectors, now, when we want to add acceleration vectors, so we have vector A here, and we have vector B here. So vector A, and we have, let's change the color for vector B, we have vector B. How would we go about adding these two vectors? Well, we can use the head-to-tail method, where we take one of the vectors and we place it on the tail of another vector, and we have to make sure that they're parallel to each other. So this is parallel to this, so we didn't change the direction of the vector. And then we simply add the vectors, right? Or for example, if we have two different vectors that are in opposite directions, so vector A again, and then you have vector B, which is in opposite direction. Obviously, this vector is negative, so when you were to add it, it would be like vector A plus negative vector B, right? Because it's in the opposite direction. And then you would add the vectors and you go about adding it like that. So the best way to represent motion is by using visuals, like graphs, for example. Like if I wanted to represent an increase in velocity, I could use a position time graph here. Like I have a graph, I have x, and then I have t. Then I have my object, its position is increasing exponentially over a certain set of time, or decreasing in this case. Now, for velocity's case, We can use other forms of graphs, like for example, a velocity time graph, where instead of x being the y value, you'd have velocity being the y value. Now, the graph will differ completely from an xt graph. Like if I were to say, for example, that this value is 0, and then here it's 10, and it reached 10, and then it's like stopped moving. So now it's like it stopped moving on an xt graph. Then on a velocity graph, you would also have to mention that it's decreasing in a negative value. So if here was the origin and its velocity, so you'd have to calculate the slope of this. Now, it if it stopped moving at around 5 seconds, then you can just take a tangent line at around, I don't know, or secant line in this case, from here to here, and then you'd calculate the slope, which would be so rise over run, so 10 over 5, which is 2 meters per second. So you get the slope, and then now you have your velocity. And now on a velocity time graph, you know the slope, right? So it would be a linear line in this case, where every 2 seconds the velocity is decreasing more and more. So here we started at a positive value and we reached a stop, right? So then we'd start at a positive value of 2 meters per second, and then we decrease all the way down to 0. Now, this is just one example of velocity time graphs and how it can represent the velocity of an object moving. There's also an acceleration time graph where instead of having a velocity represent the y-axis, you'd have the acceleration on the y-axis. And we're going to take the exact same example. So we have also here forgot to mention that it's -2 since it's negative value of decreasing. So that's why this is a downwards linear line and not like that. Now for the acceleration time graph, you'd have a as the y value and t, of course, as the x value. But because acceleration here is constant, because it's a linear line, right? The acceleration is always going to be 2 meters per second. I mean, the velocity is always going to be 2 meters per second, right? So the acceleration is going to be 0 because the velocity isn't changing. It's at a constant velocity. Thus, if I were to draw an acceleration time graph, it would be a horizontal line at 2 meters per second, or at 2. So then the acceleration is going to be 0. If we were to calculate the slope here, it would be 0. So no slope, or 0 value of slope. And those are basically the graphs. We're going to cover each graph individually right now. So for position time graphs, we'll cover the position time graphs first. We'll go through all of position, velocity, and acceleration. So firstly, let's go over the position time graphs and all their details for every kind of scenario. So for the position time graphs, we have, let's take our first example where it's a exponential function that is increasing uh, velocity. So it would be a parabola. I mean, draw it properly. And you can see here that it's speeding up. Why? Because if we take the tangent line, you can see that the tangent line is getting more vertical over time. And as you know, when it's more vertical, it's going faster, and the less vertical, it's slower. So the first detail you should know is that it's speeding up. Now, where is it speeding up? It can speed up in two ways, in the positive direction and in the negative direction. How will it speed up in the negative direction? Well, if we were to draw complete coordinate plane, and we were to mirror this parabola, then you can see here it's increasing and it's speeding up in the negative direction, as this is the negative side and this is the positive side. So it's speeding up here in the positive direction because it's in the positive side, and it would be speeding up in the negative direction if it was on the negative side. So you have to keep that in mind. So it's speeding up in the positive, so plus v direction. So we need to mention the direction. Next up, what degree would this be? Well, we know that when it's a parabola, it's a exponential function. You can see it's an exponential function simply by looking at it because it's sort of increasing exponentially over time. Like it's increasing here one and then like twice and then four times maybe six, eight times. So it's increasing exponentially. So it's to the second degree. So second degree. So x squared, for example, that's a parabola. The formula for a quadratic would be x squared. Now, next graph we have is a logarithmic kind of function where it's a parabola, but to the uh, flipped horizontally. Draw it a little properly. All right. So we have the function, and as you can see here, the tangent line, if we were to draw it, it's somewhat becoming more horizontal over time. And as you know, the more horizontal it becomes, the slower it is. The more vertical it becomes, the faster, and it's turning from vertical to horizontal. So it's slowing down. So this graph is slowing down. Now, slowing down where? Well, if we were to draw the mirrored version of it, we can see here that it's also slowing down, right? It's becoming more horizontal, but it's on the negative side of this coordinate plane, like if you draw the entire coordinate plane, and here it's on the positive side. So we know that it's slowing down in the positive VE direction, so plus VE direction. Now, what kind of function is this? Well, it's literally a parabola, but flipped horizontally, so it would obviously be the second degree. So x squared again. Now, next graph we have is same as the first one, so this one, but if it were to be up and down, something like this, if it were to be flipped side down. Now, in this case, you can see that tangent line is becoming more vertical, right? So it is speeding up, but where? Where is it speeding up? It's speeding up in the negative direction. Let's draw the full coordinate plane. You can see here that here's negative, here's positive, and it's going more negative, and it's becoming more negative, which is why it's speeding up in the negative direction. All right, and what degree is this? Well, obviously it is an exponential function, so second degree, and it's x squared, right? All right. Next up, uh we have a logarithmic function, but flipped again. So instead of being like to this side, we have to this side, like that. And just looking at the tangent line, you can see it's becoming more horizontal. And when it comes more horizontal, it's slowing down, right? So it is slowing down. Now, slowing down where? Well, if this was slowing down in the positive direction, then this would be slowing down in the negative direction. So it's in the negative direction. So minus slowing down. Here it's slowing down in the slowing. This is speeding up actually. Speeding up in plus v direction, and this is slowing down the negative v direction. Here's negative, not positive. And the final graph we have is a constant motion graph, so where the function is simply a linear line. Now, this graph, if we were to calculate the slope, we get the velocity. Calculating the slope of this gives us the velocity. Slope of this gives us the velocity. We can draw a secant here for it. Or if we want the average velocity, we draw a secant. If we want just the velocity, then we just get the tangent, and etc. So the slope of this would give us the velocity, and since it's a constant rate, uh, then we could just calculate the slope of like any point we want. We don't have to go to a specific point because the velocity is constant, right? So here it's constant motion, right? Constant motion. What is the degree? Well, it's to the first degree, right? So it's just x, y equal mx plus b, right? first degree, right? So 1. And that's it for the xt graphs. I just wanted to mention here that it's in the positive direction, so plus v direction. You have also constant motion in the negative direction if you were to be going downwards. So here it'd be negative, and it'd be to the negative v direction. So next up, we're going to be covering velocity time graphs. And for velocity time graphs, we're only going to be covering linear lines, horizontal lines, and we're not going to be covering the curved or exponential lines. So I just wanted to keep that in mind because we're going to look at 5 different velocity time graphs. So we have the first one, which is just a pretty average one. It's the linear velocity time graph where as time goes by, velocity, the value of v is increasing. So here it'd be like the value of v is increasing. So as time goes by, v velocity is increasing. It's pretty straightforward, and it's to the first degree, of course, so it's speeding up. Why is it speeding up? Because as time goes by, again, velocity is increasing. So it's speeding up in the positive of v direction. Now, why is it in the positive direction? Because if we were to mirror it like this, and we have it to that side, or to this side, if you want, then you can see that if it were to go downwards, it's to the negative direction, and if it were to go upwards, it would be to the positive direction. So you should keep that in mind to make sure you mention the direction. And then this is obviously to the first degree, so first degree, where y is equal to mx plus b. So y is equal to mx b. So a linear line. Next up, we have in the negative direction, or not negative direction, but just slowing down. So here it's a line and it's slowing down. Why is it slowing down? Because as time goes by, you have in the beginning you had 0 seconds, you had a certain amount of velocity, so xv, and then as time goes by, that xv was decreasing and decreasing until it reached 0 velocity. So it's slowing down. Now, where is it slowing down? Well, it's slowing down in the positive direction. Why is it in the positive direction? Because if you look at a mirrored version of it, where it's slowing down in the negative direction, it would be like this, where it's going upwards and slowing down in the negative direction. So here's negative and slowing down. So slowing down in the positive direction. So of course it's first degree. I'm not going to write this again because they're all going to be first degree for now. So y is equal to mx plus b. So first degree for these 4. Next up, we have slowing down or speeding up, actually, in the negative direction. Why is it speeding up here? Well, if we were to mirror this and draw it again, we saw that this is speeding up in the positive direction. So this would be speeding up in the negative direction. Because it's as time goes by, it's getting more negative and more negative until it reaches whatever point. So it's speeding up. I should erase this. Speeding up in the negative, so negative v direction. So yeah. All right, next up we have a VT graph where it is slowing down. So I mentioned it before, but we'll mention it again. So slowing down. So it's over here and it's reaching 0. So why is this slowing down? Well, if you think about it, you have a certain amount of negative velocity, and then as time goes by, your negative velocity is becoming more positive until it reaches a 0 velocity. So your velocity is becoming more positive, meaning that it's slowing down from negative to positive. And then eventually, if it were to continue going on, it'd be increasing and speeding up into the negative direction as if you had taken as if you were like moving backwards. So you're moving negatively. And then, or actually, you were moving forward. You were slowing down. So you're slowing down, slowing down. slowing down, slowing down, slowing down. And then you stopped for like a certain amount of threshold, and then you started speeding up backwards again, or in the positive direction again. So you kind of went back, slowing down. You slow down here, slow down here, and then you started speeding up again in a different direction. And then the final graph we have is a constant velocity graph, which is obviously a horizontal line, where this line is a value of 0, and it's just constantly moving at a certain amount of x velocity. So here it's constant velocity, or constant motion, you could say, and here it's slowing down in the negative, yeah, the negative v direction. And here it's constant motion, a horizontal line. If you were to calculate the slope of any of these lines, you would get an important thing, which is called the acceleration. So for velocity time graphs, slope of the line is equal to the acceleration. This is very important, so keep this in mind. Slope of velocity time graph is equal to the acceleration. So if I were to calculate this slope here and this slope here, this would give me the acceleration, which is going to be the next graph we're going to cover. So for the final graphs we're going to cover, it's going to be acceleration time graphs. You already know throughout this entire chapter, we're going to be covering constant acceleration. So there aren't going to be any curves or even linear functions, simply horizontal constant lines. So either they're going to be a horizontal line in the positive direction or horizontal lines in the negative quadrant. So for the first kind of graph we're going to cover, it's going to be a graph that looks like this, where it's a horizontal line, but in the positive direction. Now, there could be two cases for these. We're going to cover them all. So for the first case, it's going to be speeding up in the positive direction. So speeding up in the positive direct positive. So instead of writing positive, just write plus VE direction. Now, obviously, since it's a horizontal line, it will be to the 0 degree. So degree 0. Now, how will you differentiate between both cases where it's positive, where it's both in the same quadrant, where it's like there's going to be two cases, one like this, one like this. However, in this second case, it's going to be uh, it's going to be slowing down in the negative direction, where slowing down in the negative direction. So why is slowing down in the negative direction positive, right? We have slowing down and we have negative direction. Well, remember when I told you how acceleration, if you were to multiply the signs of them, then you would get a different answer for each type of case. So in this case, you have positive times positive, which gives you positive. In this case, you have negative times negative. Slowing down is negative, and a VE direction is negative. But let's actually understand the concept behind this. So if we look at a velocity time graph for a better understanding, a velocity time graph, we'll draw one here, velocity time graph. And we look at the negative side, we see that in this case, the line will be going upwards. And here it's slowing down, but if you remember the velocity time graphs, it's slowing down in the negative direction. It's slowing down, so the arrows would look like this, uh, shorter and shorter and shorter till it reaches 0, and then it would start going positive again and start accelerating or start uh, becoming more positive over time. So here it slows down over here because it's becoming more and more positive because here it's negative, right? and then you're adding more positive values until it becomes 0. And then it starts continuing to go positive and more positive and increasing. So that's why it's slowing down in the negative v direction and it's in a positive acceleration. And for the speeding up in the positive direction, it's pretty simple. You're just speeding up in the positive direction. So like if this was +2, then you'd continue going +2 meters per second squared and continue to go +2 meters per second squared over the constant acceleration. Now, for the next two graphs, we have two negative graphs where if we were to draw it over here in the negative coordinate and it goes in a straight line like this. And this one, we can call it slowing down in the positive direction in plus VE direction. Now, as you know, slowing down is negative, and plus V direction will be a positive acceleration, and negative times positive gives you negative, which is why it's in the negative quadrant. Now, if you wanted to understand this better, then the velocity time graph of this would look like this, where the velocity line, so Vt, would just be going down, so it's slowing down in the positive quadrant. It's pretty simple, which is why the acceleration is negative, because it needs to be a negative sign, because it needs to be a negative acceleration for it to slow down like this. Now, for the next graph, we should know the difference between these two and when each case is being done. So in this case, we have uh, speeding up in the negative VE direction. So speeding up is positive and negative v is negative acceleration, so plus times minus. It's going to be negative. So how would a graph speeding up in the negative direction look like for velocity? Well, to understand it better, then we draw it like this. So vt, and then your velocity line would look like this, where it's going more and more negative. So it's speeding up more negatively. So you'd add more negative to it, plus. So it's at a constant -4, -6. So it's increasingly becoming more negative, which is why it's speeding up in the negative v direction. Now for the final graph, it's going to be a constant. For the final graph, it's going to be a constant motion graph where the acceleration isn't changing at all. And when the acceleration isn't changing at all, then it's going to be a horizontal line at the 0. So constant motion. So remember, when the velocity is not changing, no change, acceleration is also, this acceleration will be equal to 0. And that will be it for the acceleration time graphs. So here we have a velocity time graph. During your quiz, you should make sure that you know which graph you're dealing with. So you should like take a look at the x and y axis to make sure you're dealing with the certain graph. Because if you think of this as a position time graph, you're going to have completely different results if you were to deal it with a velocity time graph. So we have a velocity time graph here. And our first question is, where is the acceleration on this graph? 0. So meaning that there's no change in velocity. So if there's no change in velocity, that means the velocity should have a horizontal line. So horizontal line here, horizontal line here, horizontal line here, and a horizontal line here. So that your answer would be AB, CD, EF, and GH. So these are the lines that give you a 0 acceleration or no acceleration at all. Next up, we're going to ask where in this graph is the acceleration greater than 0? Now it's important to note greater 0, not just there's acceleration. When is it positive? So positive v acceleration. If you remember from the graphs before, we mentioned that time goes by, uh, velocity is increasing, and as time goes by, uh, uh, as time goes by here, velocity is increasing. So we have 2 points on this graph where there's acceleration. But where's the acceleration positive? It should be over here, g and f. Why? Because if we were to find the slope of this, it would also be positive. If we were to find the slope of this, it would be negative. So it's just from f to g. So our answer would be f, g. This is the only point where there's positive acceleration. Now, finally, at which point is our acceleration negative? Well, we would say that it's from d to e. So d to e, because it's going downwards into the negative direction. Finding the slope of this would give us a negative value, not a positive one. And that is it for this question. So for this next question, we need to understand the difference between instantaneous velocity and the average velocity. So instantaneous velocity versus average. So average velocities. So what is the difference? Well, instantaneous velocity is calculated using a tangent line. So just calculating the slope of the tangent line will give you the instantaneous velocity. It is the velocity at one point. Now the average velocity is the velocity throughout 2 points, which is why we'd use a secant that connects two different points with each other. Which is why when you do calculate the average velocity, you need to do rise over run with a secant line. When you calculate instantaneous velocity, you should also do rise over run. You're calculating the slope. So for this question, it's asking to find that instantaneous acceleration at 30 seconds. Now the secant line is drawn for the tangent line is always going to be drawn for you if they ask you about it, because everyone can have a different tangent line. Like you can kind of draw like this or draw like that. No, tangent line can differ, so that's why they will have it given to you already. And yeah, so just do rise over run. We can take like 2 points. We'll take this point and take points given. So rise, let's change color. So rise over run, which is y1 minus y2, y2 minus y1. So y2 is 260 minus 210 over 50 minus 0. So it's going to be 50 over 50 is equal to 1 meter per second squared. So this is the instantaneous acceleration. Oh, I meant here acceleration, not velocity. My bad. So this is the difference between instantaneous acceleration and velocity, and instantaneous acceleration and average acceleration. So to find the average acceleration between 10 and 50 seconds, we'll draw a secant line between 10 seconds, so here, and 50 seconds, which is right about here. And we can draw the line just like that. And then we'll calculate the slope of this line to find the average acceleration. So again, same exact thing, rise over run. So 250 over, so 250 over 210, and then 50 minus 10. 50 minus 10. That'll give us 50 over 40. So here it's a 40 over 40, not 50 over 40. So 40 over 40. 1 meters per second squared. So that's the average acceleration. Just find the secant line, and then we calculate the slope. Same with instantaneous acceleration. So that is how you find these two values. For our next question here, we have a velocity time graph. So velocity time graph. And we want to calculate a few questions here. Before that, let's actually interpret this graph and understand it. So, firstly, what can we say about its velocity? Well, we can say it's speeding up, right? Because as time goes by, the velocity is increasing. So it's speeding up. Where is it speeding up? Speeding up in the positive direction. Up in the plus v direction. So, secondly, what can we say about its acceleration? Well, if we were to calculate the slope of this, it would give us the acceleration, and no matter where in a linear line you calculate the slope, it would be the same value. So meaning that the acceleration here is constant. So acceleration is constant. Constant acceleration. All right, now to the questions. What can we say about the initial velocity of this velocity versus time graph? So if we were to look at the initial velocity at t equals 0, we would see that the velocity is also equal to 0. So it's 0 meters per second. Secondly, what is the velocity after 1 second? So after 1 second, we can look at the point over here, and it's at 1 meter per second. So we can say 1 meters per second. Velocity after 3 seconds, we look up here and we find it at 3 meters per second. So 3 meters per second. And at 5 seconds, we look up and we see that it's at 5 meters per second. So 5 meters per second. Now for question C, it's asking for rate of change of velocity. So when we talk about rate of change, we're talking about the slope. And we already know the slope here. If we just simply do rise over run, any 2 points, we can get 1 meters per second. So that is the acceleration here. As you know, the slope of the velocity time graph of VE, VT is equal to acceleration. So the rate of change here is the slope, and after 2 seconds, the rate of change doesn't change. It's constant. It's at constant velocity, right? Or it's at constant acceleration. So the rate of change of velocity will still always be 1 meters per second. What is this rate of change after 5 seconds? The velocity, the rate of change here didn't change. It didn't curve up, it didn't curve down, it didn't become horizontal. So we can still say it's at 1 meters per second. So when it talks about rate of change, we should calculate the slope. That'll be it for lesson 3.1, acceleration. If you have any questions or want to ask anything at all, you can ask it down below in the comments or in the server. If you want more tutorials on physics or math or any other subjects, you can find them on the channel, and enjoy them.